So the thing is, because you're sweeping through and it always starts from the origin, just going from there all the way out there includes all of this stuff too. Right? Because you're sweeping out all the way here from the pole out to the curve. So that's too much. The blue is way more than just what I have there shaded in with my highlighter. So then you'd have to subtract off going out, and I didn't do it here, but let's go ahead with red. So do you see how purple is blue minus red for this example? So this is my the purple, which is the total area I'm looking for, is equal to the blue minus the red. That's what you would plug into your calculator to get the answer. Yes?
Can you include it in like the same interval? Like can you just do r1 squared minus r2 squared?
Great question. When you have the same exact limits of integration, you can combine that so it's 1/2 times the integral from 0 to pi halves of r1 squared minus r2 squared d theta, for sure. But the limits of integration have to be exactly the same in order for you to combine. Yes?
Could you number 20?
I might not be able to get through all of this. Okay, so the interesting thing about this is, do you all see that the area of that orangish region over here is going to be the same as the area of the orangish region over there? Because I have this peanut looking guy, and if you spin it, the area is going to be exactly the same. And then that flower looking guy is exactly the same. In fact, it's the exact same curve r equals sine of 2 theta. So as long as this doesn't go outside of that or anything weird happens there, then it doesn't matter how you turn that peanut looking guy, which is the either 2 plus cosine 2 theta or 2 plus sine 2 theta. It doesn't matter how you rotate that, you're going to have the same area that's inside, right? So for this, the way that somebody might think about this is, hey, find the area of the peanut guy just by itself, minus the area of that flower guy all by itself, right? And then they might say, well, the peanut is really, this peanut is symmetric, so really I could only go from 0 to pi halves and then multiply that by 4, and then this is really, it's going to look like, it's going to look like that. So really, if you just look in the first quadrant and you find the area of the peanut guy in the first quadrant minus the area of the flower guy in the first quadrant, and then got that value and multiplied by 4, it's like just reflected about different axes, and it's going to give you the same answer. Do y'all see that? That's how I would approach it. So I would start with the area of the blue. Did I copy this already? Yep. Yeah, so I would say the total area equals 4 times, and then here it's going to be, if this is r sub 1, and then this red one is r sub 2. I would verify, first of all, that r sub 1 is going to be from 0, theta equals 0 to theta equals pi over 2. and then that's going to be the same for r. So 2. So I'm going to plug that in. 2 plus cosine 2 theta. And the other guy is sine of 2 theta. And my window, I'm going to go from 0 to pi over 2. And let's just graph these guys and see what we got. So I have, I didn't go out far enough for my,
What did you put cosine 2 theta?
I'm just using this guy. It doesn't matter which one. But I didn't go out to, on my window, I should have gone out to 3. So, to really see it, it should look like this. So there it goes, right? So anyway, do you see how it's going, that the limits of integration are going to be from 0 to pi halves? And then I'm going to multiply that by 4. So over here, it's going to be 0.5 or 1/2 times the integral from 0 to pi halves of r1 squared minus r2 squared d theta. So really, that's going to be just 2 times the integral from 0 to pi halves of r1 squared minus r2 squared d theta. Does that make sense? Cool. Tonight's homework, so I gave you the new February